All right, welcome back, everybody. This is MTED110, and today we're doing lecture 11C. So we're going to finish chapter 11 today. This is the one where we do all of the divisibility tests, and we're going to prove all of them just so that we can actually know for a fact that they are true and understand why they're true. We don't have to believe that they're true, they're actually true. And it's also really amazing because the divisibility tests they basically link numerals to the number in very interesting ways. And my favorite proof is the divisibility test for 3, which we'll see very soon here. Okay, let me go ahead and pull up the slides. This is where we left off. Then let's start with the divisibility test for 2. We're going to collect them all. 2, 3, 4, 5, 6, 8, 9, 10. 10 is an easy one, right? Once you have 5, you have 10 and 12. We're not going to do the divisibility test for 7. There is one, and you can look it up, but it's not very straightforward. It's one of those things where it's like if you do this, if you like divide this and then add this to it, then you know it's divisible by 7. But you can look that up if you would like. All right, so this is the divisibility test for 2. It says that a number is divisible by 2 if and only if 2 is a factor of the ones digit. So in other words, the ones digit has to be a 0, 2, 4, 6, or 8. In other words, the ones digit needs to be an even number, right? So if 2 is a factor of a number, then that number is even by definition. So let's prove this. Why is this actually true? Who says this is true, and why does it work? How can we determine something about the number just by looking at the numeral at the very end, right? That's kind of bizarre. So let's see the proof. First, we're going to let n be any natural number. And I'm about to throw up a funky looking expression here, but don't be overwhelmed. Just take a deep breath, okay? We're going to write this number n in expanded form. So remember back in chapter 2, actually, you know what? Just take a moment and just look at that and think about it. See if you can figure out what it's showing. Okay, now let's talk about it. It seems overwhelming, but it's just that expanded form. It's the same thing as that expanded form we saw back in chapter 2. Oh wait, I mean back in chapter 2. Except now we don't know how long of a number n is. N could be 1,000 digits, it could be 1,000,000,000 digits, but we can always write it in this expanded form. So let me just kind of emphasize here. Uh, Notice here that you have the powers of 10. 10 to the 0, 10 to the 1, 10 squared, 10 cubed would be in here. But then we don't know how many powers of 10 we're going to need, right? We may need to have 10 to the 100 for all we know. So that's what this is representing right here. This is basically the last power of 10 that you would need. So this could be like the thousands place or the 10,000s place or whatever, right? So these are all the powers of 10. M minus 1 is just the previous power of 10, or I should say the previous power of 10. That's all it is. Then right over here, all the little D sub letters, those are just the digits. Those are the digits 0 through 9. So that's a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. That's a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. That's a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. That's a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. It's just that same structure, right? So I hope you can see that. I think we commonly use a number like this, and we would say 2 times 10 cubed plus 3 times 10 squared plus 6 times 10 to the 1 plus 7 times 10 to the 0. And there you go. So once again, this is why chapter 2 is so important, because everything relies on our numeration system. And that makes sense. We're trying to prove something about a relationship between a numeral representation and the number itself. So we're going to need to use this representation, right? Okay, so I hope that makes sense. If that doesn't make sense, I will happily explain it more in the collaboration meetings. Okay, so every term before this one, the very last term, has a factor of 10 in it. Let's look. You can see it, right? Uh, Here we go. This number, whatever this number is, it's got a factor of 10. Whatever this number is, it's got a factor of 10. Whatever this number is, it's got a factor of 10, and so on and so on. So every one of those terms has a factor of 10 in it. So that means that they're all divisible by 2. Why is that? Because we know that if 2 divides a number, then it divides any multiple of that number, right? So I know that 2 divides 10. 2 definitely divides 10, so that means 2 divides any multiple of that number. say, oh, 100 or even 200 or any multiple. And that's what these are. All these terms are multiples of 2. They're multiples of 2. So that means they're all divisible by 2. So then all we have to do, oh, by one of our previous theorems, sorry, I forgot this one. Yeah, by one of our previous theorems, this whole sum, oops, this whole sum is divisible by 2. It's divisible by 2. Because remember, if 2 divides one term and 2 divides another term, then 2 divides their sum. That's exactly what we're talking about here. So we needed that theorem to actually prove this divisibility test. And there it is. This is divisible by 2 plus this thing divisible by 2. So this is divisible by 2. And then you just keep adding them all up. So we know for a fact that this thing in the box is divisible by 2. So then, if we want to know if the whole number is divisible by 2, all we have to do is check the very last number here. And if that number is divisible by 2, and we know that this is all divisible by 2, then the whole thing is divisible by 2. That's the idea. All right, I hope that makes some sense. If it doesn't, I can explain it again. But now, what does this thing represent? 10 to the 0 is 1. Let me pull this out. 10 to the 0 is 1. So d sub 0 is, I'm sorry, d sub 0 times 10 to the 0 is really just d sub 0. But d sub 0 is just the ones digit. It's whatever digit is in the ones place, right? And so what we're saying is that this number will only be divisible by 2 if the ones digit is divisible by 2. That's what we were trying to prove. That's what we were trying to prove, right? So in other words, if that ones digit is a 0, 2, 4, 6, or 8, then the whole number is divisible by 2. And that's the proof. That's the idea. So yeah, again, I hope you can appreciate how important this expanded representation is and how important those previous theorems were in the last lecture, right? We needed those to do this. Oh yeah, there you go. D sub 0 represents the ones digit of, oh, sorry, that should be an N, not an A. There we go. So we are done. And there's my little proof symbol. End of proof. Sweet, huh? All right, so that's the divisibility test for 2. You do need to have that memorized. You don't need to memorize the proof. You don't need to memorize the proof, but I hope you at least followed it. You should be able to follow the proof, but you don't need to memorize it. You do need to memorize the divisibility tests, though, all of them, all of them. So the divisibility test for 5 says this, moving right along, right? A number is divisible by 5 if and only if 5 is a factor of the ones digit. Or in other words, the ones digit is a 0 or a 5. And what's the proof? The proof is nearly identical to the previous one, right? So we're not going to go through it. It's virtually identical, except now you just have to check to see if this is divisible by 5, because every single one of these terms is already divisible by 5, because each of these has a factor of 10 in it, and 10 has a factor of 5 in it. So all these things, that whole thing's divisible by 5 already. You just got to check the last bit. Okay. Moving right along, the divisibility test for 9. This one is actually my favorite. I said 3 before, but really I meant 9. And what you're going to see is once we get 9, we get 3 for free. So this is really bizarre. And if you've never heard about this, I hope this will blow your mind a little bit. But it says that a number is divisible by 9 if and only if the sum of the digits is a number divisible by 9. So this is really weird because it basically means you add up all the digits of a number, and if that new number you get is divisible by 9, then the number you started with is divisible by 9. Let's see, do I have examples here? Yeah, exactly. 72, that's divisible by 9 because if you add the 7 and the 2, you get 9, which is divisible by 9. Weird, huh? Or this one, the number 123,444, that's divisible by 9 because if you add all those digits up, you get 18. And 18 is a number that's divisible by 9. So that means that this is divisible by 9. What? How bizarre is that? How wild is that? You know what's even cooler? One of my students pointed this out a couple semesters ago. If you're not sure, let's say you've got a big number and you end up with this number and you're not sure if it's divisible by 9, you can just repeat the process. You can just repeat the process again. Add up these two numbers, and if I add up 1 and 8, oops, getting ahead of myself, I get 9. So you can keep going. Isn't that wild? But why does that work? Why does that work? Who says that works? I don't believe it. I don't believe that at all. I mean, that's cute and clever, but I'm not going to believe that. And we don't have to, because we're going to prove it right now. Just for clarity, we're just going to use a four-digit number. We're not going to do the arbitrary expansion like we saw for the divisibility test for 2. We're just going to do a four-digit number because I think that really makes it clear what's going on. So here's the proof. Let n be a whole number, and we're going to let it be represented by the numeral a, B, C, D. Okay, so in this case, A, B, C, D are just representing some digits 0 through 9. So our number could be like 2, 3, 6, 7, or 1, 4, 9, 8, or 2, 1, 6, 6, or something like that. But we're just going to say it's A, B, C, D, because we don't know what those digits are. All right, now, like before, we can write it in expanded form. It all relies on that expanded form, and we're going to notice something interesting. So let me try to go line by line here if I can, because this is, actually, I'll leave it like that. First, this is the expanded form of n. Right? And now hopefully you can see the structure, because here's the a times 10 cubed, and then you've got b times 10 squared, and c times 10, and d times 1, right? So there's the expanded form. And now what we're going to do is we're going to be a little bit clever. We're going to be clever because I can rewrite 10 cubed as 999 plus 1. That's all I'm going to do there. Just rewrite 10 cubed as 999 plus 1. But I can also rewrite 10 squared as 99 plus 1. So I'm going to write 10 squared as 99 plus 1. And then similarly, I can write 10 as 9 plus 1. And then I can also write, actually, let me pick, here, I'll use green. I can also write, actually, this is just the same. I can write 1 as 1. We'll leave that. All right, so what I'm going to do now is I'm just going to use the distributive property. And I'm going to distribute this A to both of those terms, and that B to both of those terms, and that C to both of those terms. And once I do that, that's where I get A times 999 plus A. A times 1 is A. B times 99 plus B. B times 1 is B. C times 9 plus C. C times 1 is C. And then over here, it's just D, because this is already equal to 1, right? All right, so now look at what we've got here. Get my little highlighter out again here. So we've got A times 99, B times 99, C times 9, and then we have a bunch of these individuals right here. So I'm just going to commutative property of addition, right? Shifting these quantities around physically in my mind. And I'm just going to put all of the these multiples of 9 over here. Kind of gave it away right there. A times 99, B times 99, C times 9, and then we just have all of these little individuals over here. Okay, the very last line is just me minimizing the notation. So this is still 999 times A, 99 times B, 9 times C, and then that collection, all right? So this is the decomposition we need. Now here's the clever part. We've rewritten n like so. Now the first 3 terms, this one, oops, this one, and this one, those are all divisible by 9 because those are all multiples of 9. And as a result, their sum is divisible by 9. Div by 9. Okay? So the sum is divisible by 9. So in order for n to be divisible by 9, we need this to also be divisible by 9. Because if this is divisible by 9, and we already know this is divisible by 9, then the whole thing is divisible by 9 by that theorem we saw in the previous lecture, right? That's what's so cool. All right, but here's the interesting part. What does this represent? Like this part is all good. We know that that's divisible by 9, but what does this represent? We just need A plus B plus C plus D to be divisible by 9. Huh. But look at that. A is the first digit that we solved. A was the thousands digit. B was the hundreds digit. C was the tens digit. And D was the ones digit. So what we're saying is that if this number is divisible by 9, or you can tell if this number is divisible by 9 by just adding up all the digits. And if the sum of those digits is divisible by 9, then the whole thing is divisible by 9. But that's what we were trying to prove. That's what we were trying to prove. The sum of the digits must be divisible by 9. So that's super cool. It makes it really easy to determine if something is divisible by 9. That's really what it is. I love that. I love that proof. I love that. This is just such a clever deconstruction. And again, you should take some time just to look at that and make sense of it because of how clever it is. It's really awesome. Um, anyway, I'll stop there. Uh, so the divisibility test for 3, funny enough, is exactly the same. The divisibility test for 3 says if the sum of the digits is divisible by 3, then the whole number is. And the other way, a number is divisible by 3 only if the sum of the digits is divisible by 3. The proof is identical to the one for 9. So we're not going to do that. It's virtually identical. The reason, again, is because, I'll use this page here. The reason is because each of these is already a multiple of 3. That's divisible by 3, that's divisible by 3, that's divisible by 3. So if we want to know if the whole number is divisible by 3, we just have to check that that's divisible by 3. That's the proof. So we've already done it. All right, moving right along. Let's do the divisibility test for 4. And we're going to prove this one too. So the divisibility test for 4 says a number is divisible by 4 if and only if the number formed by the final 2 digits is divisible by 4. So that's kind of funky. I don't know if you've seen that one before, but that's interesting too. So for example, this number, 1,368,948, that's divisible by 4 because the last digits form the number 48, and 48 is divisible by 4. So we know that the whole thing is divisible by 4. That's what that says. Okay, this number, 768,972, that's divisible by 4. Why? Because this number here, 72, is divisible by 4. Okay, so why does that work? Like, why does that work? Again, like, it's really bizarre. How is this working? Why is it that we can just ignore the rest of the number and just look at the last 2 digits? That's so weird. Um, oh yeah, also notice a number is divisible by 4 only if it's divisible by 2, because 4 is a multiple of 2. So if you're divisible by 4, you're definitely divisible by 2. Okay, so let's see the proof. And again, we're going to use a 4-digit number just because it kind of makes sense that way. And again, we're going to write this number as A, B, C, D. So those are just the digits, A, B, C, D. It could be the number 2,367 or 125 or 1,125 or something like that. All right, excuse me. So just like before, we can write it in expanded form. A in the thousands place, B in the hundreds place, C in the tens place, and D in the ones place. Now, here's the cool part. We know that 4 divides 100, and that's because we can write 100 as 4 times 25. Remember, this is the definition of what it means to be divisible, right? I can write that number as a multiple of the divisor. That's what it is. You see, there's all that terminology, all that vocabulary, factors, divisors, multiples. But here's the cool part. We can write this as AB00 plus CD. So for example, if I had 2,367, I could write it as 2,300 plus 67, right? So that's what I'm saying down here in this funky notation right here. The AB would just be the 2, 3 in this case. And the 0, 0 would be the 0, 0 right here. And then you've got the remnant, CD. So here's the cool part. We know that 4 divides 100, but this number right here, that's a multiple of 100. And by a previous theorem, we know that if a number divides another, then it divides all multiples of that number. So that tells us that this is already and always going to be divisible by 4. It's a multiple of 100, no matter what it is. Even if I wrote something like 6, 5, 9, 8, 1, 2, even if I wrote that, right? If you shave away this part right here, and shave away that part, move it over there, and just write it as 100 plus that, then this number is guaranteed to be divisible by 4 because it's a multiple of 100. It's just a lot of hundreds. It's a heck of a lot of hundreds, right? But it still works no matter how long the number is. So then that means that we know that the whole number, A, B, C, D, will be divisible by 4 if the little digits at the end is divisible by 4, the number formed. So if CD is divisible by 4, then the whole thing's divisible by 4. Because all the previous stuff is already divisible by 4. Pretty cool, huh? I think that's pretty cool. All right, so for example, these are just more examples to illustrate it. 56,744, you can split it up. like so. We know that 4 divides 56,700. That's definitely true because it's a multiple of 100. We also know that 4 divides 44. And if a number divides two terms, then it must divide their sum. Ah, isn't that cool? I think that's cool. That's why we needed those theorems, man. That's why we needed them. These are just some more examples if you want to go through. Now we're going to truck right along and go to the divisibility test for 8. So 8 is very, very similar. So let's check it out. A number is divisible by 8 if and only if the number formed by the final 3 digits is divisible by 8. Wait, what? Why is that? That's weird. It's like the same thing as 4, except now we're going out an extra digit. Hmm, Why is that? That's very strange. Well, uh, the proof is virtually identical to the divisibility test for 4. Let's go back and look. So let me go back to this bit right here. Okay, so what we did in this proof was we wrote n in this expanded form. And what we're saying now is you just have to look at these last digits. And if those digits, or the number formed by those digits is divisible by 8, then the whole number n is divisible by 8. Why is that? Well, the reason is because this guy is always going to be divisible by 8. Yeah, remember? Sorry, 10 cubed is 1,000, and 1,000 is divisible by 8 because 1,000 is equal to 8 times 125, right? You can count them, 125, 250, 375, 500, there's 4, do that again, you'll get 8, right? So anything above, basically all this and beyond, those are all divisible by 8. That whole sum is divisible by 8 already, so you just got to check the last 3 digits. That's the whole idea, right? So I hope that makes sense. If it doesn't, I'll be happy to explain it more. Um, yeah, so what's really cool is that the method in that proof can be generalized. It can be generalized to a general divisibility test for any power of 2. And the reason this is so cool, I think, is because one of my previous MTED students figured this out. We were talking about the divisibility test for 8, and I had asked the class, like, oh, what do you think we're going to do? And she just very quickly was like, oh, you're going to look at the last 3 digits. And I was like, how did you figure that out? And she goes, well, for the divisibility test for 2, we looked at the last digit. And for the divisibility test for 4, we looked at the last 2 digits. And for the divisibility test for 8, we're probably going to look at the last 3 digits because all of those things have a multiple of 8 in them, everything above that, right? And then I was like, huh, that's actually, I think that's correct. And then what we did was we looked back at the expanded form in this proof, and we were like, oh yeah, that method will continue. The method of that proof can be extended to any power of 2. So here's the generalization of that divisibility test. And you don't have to memorize this one. That's okay. But you'll also see that it doesn't, it loses, what's the word? It loses practicality, I'll say. It loses practicality once you get pretty large, once you get large numbers. But a whole number is divisible by some power of 2, as in 2, 4, 8, 16, 32, 64, and so on, if and only if the k rightmost digits of the whole number represent a number that's divisible by 2k. So basically just look at the last 2k digits, and that'll tell you if it's divisible by 2k or not. And actually, so once she came up with this, I, again, didn't want to believe it because we shouldn't believe it, right? We should be able to prove this kind of thing. And so what I did was I went ahead and I did a rigorous proof back then. I'll pull it up right here. Yeah, so this is the rigorous proof. If you want to read it, you can. If you're interested, I can explain it. But this is the rigorous proof of that theorem. And it's funny because it also relies on this other lemma down here. You need this lemma to actually prove this theorem. And this is kind of a handy lemma to know. It says if b divides a number a, then b to the k divides the number a to the k. Another handy divisibility theorem there, right? You don't need to know this stuff, but I just wanted to show you that even students at MTED110 can come up with these amazing theorems just by using repeated reasoning and making sense of the structure of these numbers, right? It's really just really cool, I think. Okay, I'll stop gushing about it now. Okay, so where were we? Okay, so the divisibility test for 6. A number n is divisible by 6 if and only if it's divisible by 2 and 3. And that's exactly what we were talking about earlier on in the lecture, because I was saying that that number was divisible by 6 because it was divisible by both 2 and 3, because 2 and 3 appear in the prime factorization. Um, the proof of this is a combination of the divisibility tests for 2 and 3. So the one that I gave at the beginning was kind of where I was relying on the prime factorization. You can do a different proof here if you combine the proofs that we saw earlier. Okay. Oh, and also the converse holds. All right, so in general, what we can do is we can leverage previous tests to construct new ones, but only under specific circumstances. And so now we need this definition, and we're going to get back to that asterisk here. So this is a definition that you do need to memorize. You need to be comfortable with this. But we say that two numbers m and n are relatively prime if they have no prime factor in common. No prime factor in common. So I'll give you an example. 2 and 3 are relatively prime. 2 and 3 are relatively prime because they don't share any factors in common. However, a number like 2 and 6, those are not relatively prime because 6 is equal to 2 times 3. And so what happens here is they share a common factor. They share a common factor. So that means they're not relatively prime. They're not relatively prime. That's actually why this word relatively is so nice, right? It makes sense. They're not, we're talking about primality relative to each other. There you go, right? So 2 and 6 are not relatively prime. 2 and 3 are relatively prime, and so on. So here's where that asterisk comes back into play. Here's where that asterisk comes back in. Because remember, we were looking at that one question, and for some reason it was false. It was like, oh yeah, if 2 divides a number and 6 divides a number, right? 2 divides a number and 6 divides a number, then 18 divides a number. And we were like, is that true or is that false? And it turned out to be false, right? And the reason for that is because 2 and 6 are not relatively prime. They share a common factor. And because of that, this statement is not true. So we can leverage that. We can still get a statement out of that. We just have to be more careful with what we say. And so what we're going to say is this instead. If m divides a number and n divides a number, and m and n are relatively prime, like 2 and 3, then mn divides that number. The product divides that number. So that's what you need. That's what you need. And what's handy about that is we're going to use this to get a divisibility test for 12. Yeah, there you go. So for example, is 108 divisible by 12? Well, I don't know. Let's think about it. Think about it. Is 108 divisible by 12? Hmm. Let's do this one together. Well, I know that 808 is divisible by 4. So I'm looking at just the last digits here. And that's divisible by 4, which means that 108, oh, sorry, this is divisible by 4. And the sum of these digits is 9, which is divisible by 3. So that tells us that this number, 108, is divisible by both 4 and divisible by 3. But if it's divisible by 4 and it's divisible by 3, and we can notice that 4 and 3 are relatively prime because they don't share any common factors, that means that 108 must be divisible by 12. Yeah, because 3 divides 108, 4 divides 108, and 3 and 4 are relatively prime, so 12, their product, divides 108. There we go. So it's divisible by 12, and that's the divisibility test for 12. But it's really just a special case of this general divisibility test for any product. You just need to think about relative primeness, all right? Okay, so yeah, exactly. So divisibility tests can help us find the prime factorization of numbers. So let's try 12,320. Yeah, it's divisible by 2 and 5 because the ones digit is a 0. So we know it's divisible by 2 and 5. It's also divisible by 4 because the last two digits are form a 20, and that's divisible by 4. It's also divisible by 8 because 320 is divisible by 8. It's not divisible by 3 or 9 because if you add up all those digits, you don't get a number that's divisible by 3 or 9. And leveraging these facts lets you compute the prime factorization. So you can realize right away that you can start factoring out 2s and 5s, right? and that'll help you get the factor tree and the prime factorization. So this is what it is in the end once you factor that number, and that's why we like these divisibility tests. All right. Okay, so now testing for primes. This is where cryptography kind of comes in, right? We want to know if a number is prime. So imagine I gave you like a gigantic number. How do you know if it's prime? How often do you need to test? Like let's think about oh, I'm sorry. I should read this before I go off. It says when testing to see if a number is prime, you need only test for divisibility by a prime number. Why is that? Think about that for a minute. All right, now speak out loud about what you were thinking to yourself, to a ghost, to the wall, to your group members. Okay, now let's talk about it. We only need to test divisibility by a prime number because of the fundamental theorem of arithmetic, which says that every number can be written as a product of primes. So if we want to know about divisibility, just test for primes. Um, Yeah, so but even so, this can be very tedious for numbers like 79 because if we want to know if a number is divisible, or sorry, if we want to know if 79 is prime, we've got to test a lot of divisibility. I mean, and if we only have to use prime numbers, that cuts down the work a lot, but not a ton. I mean, how many prime numbers are less than 79? Let's go through. 2, 3, 5, 7, 11, 13. 17, 19, 23, 29, I believe is the next one. I mean, man, that's a lot of numbers. I got to test divisibility by all of these just to see if that number is prime. Oh man, that's gonna be painful. Oh yeah, there you go. So 71 has 21 prime numbers that are less than it. So this list would be 21 items long. Oop, shoe just came off. Um, So here's the question. Do you think we need to test divisibility by all 21 of them? You can probably guess that the answer is no. There's a shortcut. There's a shortcut. And the shortcut is given to us by this theorem. And this is kind of a technical theorem, so it takes some time to wrap your head around it. It says when testing a number for primeness, you only need to test divisibility by all primes less than or equal to the square root of that number. So basically, if we're trying to test if 79 is prime, we don't have to do all the primes up to 79. We just have to do all the primes up to the square root of 79, which is really, really handy because the square root of 79, let's see, what's the nearest square? 81 is 9 times 9. So really, we only need to test primes up to 9 if we wanted to be safe. And that's easy, right? How many primes are there before 9? 2, 3, 5, 7. So you test those 4 prime numbers, and that'll tell you if 79 is prime or not. Okay, but again, do you believe me? Why is that? Why does that work? You shouldn't believe me. We should prove it. So what we're saying is you only have to test up to the square root of that number, and let's see why. The proof is actually quite quick. It's like one line, but it's conceptually deep, so you have to really ponder what it means. Um, so if you've got numbers p and q that are bigger than 1, if p is larger than the square root of that number and q is larger than the square root of that number, then their product is larger than the number itself. I'll just say that. So basically, if p is bigger than the square root of n and q is bigger than the square root of n, then their product is going to be bigger than the number that you're considering. So what that means is that either one p or q must be less than the square root of n if either of them are going to be factors of n. So basically, if those numbers are bigger than the square root, then it's like you overshoot the number that you care about. So that means you only need to look at numbers that are less than the square root. Numbers that are less than the square root. That's the only way that they can actually be factors of n. All right, so again, like I said, it's a very quick proof, but it's conceptually deep. So you have to kind of think about what it means for those numbers to be factors and for them to be prime factors. And we can talk about it some more in the collaboration meeting if you want. But yeah, so here we go. I just said this earlier. The square root of 79 is less than the square root of 81, which is 9. This means we only need to check divisibility by the prime numbers less than or equal to 9 In other words, just test it by those four numbers. So let's check. Does 2 divide 79? No, 79 is not even. Does 3 divide 79? What are the digits? 7 plus 9 is 16. 16 is not divisible by 3. Boom. What about 5? No, 5 definitely doesn't divide 79 because it doesn't end with a 0 or a 5. And 7, that one, well, we didn't learn that divisibility test, but let's just think about it. I know that 7 times 11 is 77, but, so I'll say this. So 7 divides 77, but 7 does not divide 2. So that means that 7 does not divide 77 plus 2, or in other words, 79, right? There you go. There you go. There you go. So that's why we needed those other theorems that the book didn't include, because it lets us do things like that very easily. I just found a multiple of 7 that was really, really close to 79. And then I looked at the difference of the two and I was like, oh, well, 7 doesn't divide that difference, right? It doesn't divide the difference between 79 and 77. So it can't divide 79 because it would have to divide that difference. If it was, because remember, if it divides one and it doesn't divide the other, then it's not going to divide the sum. Same deal right there. That's why we need those tests, or those theorems, I mean. And that's why I was saying you don't need to memorize them, but they really come in handy. Okay. Oh, yeah, there you go. There you go. Oh, yeah, there you go. Actually, I did it a different way. I looked at 7 times 11, which was 77, and 7 times 12, which is 84. But 79 is between, right? 79 is between 84. Actually, I shouldn't use that notation. That's bad notation. 79 is between those, and I only went up by, oops, and I only went up by one multiple. So guaranteed, doesn't work. All right. So 79 is a prime number. Yep, that's a prime number, and we just found out. Wait, did I? Oh, there we go. I just said that a second ago. This is the one that I just did first. So 7 divides 77. 7 doesn't divide 2, so it can't divide 79. All right, fun stuff. Very, very fun stuff. And this one, I'll let you do this one on your own, since now you kind of get the idea. What's the largest prime that we need to worry about to determine if 119 is prime? Think about it for a minute. Okay, now say out loud what you were thinking about. Say it out loud. All right, and let's see if we can do this one. I think I have it. Oh, no, I didn't. Yeah. All right, do that one on your own. If you want, I can do it in the orientation meeting, but you should try it on your own. All right. Oh, okay, so we're almost done here, actually. The very last thing we got to talk about are these: greatest common factors and least common multiples. This is one of the reasons I moved chapter 11 forward in the curriculum, or I should say forward in the curriculum, because here we need these concepts to play with fractions effectively. That's the idea. And students will learn about these concepts before they learn about fractions anyway. But here we get to learn about them in a very, very rigorous way, and also with an eye on the horizon. You'll see what I mean in a minute here. So first off, the greatest common factor of two or more whole numbers, the greatest common factor, is the largest number that's a factor of all the numbers. It's also called the greatest common divisor, or GCD. So GCF or GCD, this is the biggest number that divides all of them. Okay, that's what the greatest common divisor is. So if I give you two numbers like 112 and 68, my question is, what's the biggest number that divides both of those numbers? That's what we want to know. That's the greatest common factor, or the greatest common divisor of those two numbers. Yeah, so for pairs of small numbers, the greatest common factor is easy to see right away, or easy to see right away. So for example, the greatest common factor of 8 and 12, that's 4, because 4 divides 8, 4 divides 12, and there isn't a bigger number that divides both, right? But what about a number like this? There we go, like the ones that we did. How would we find the greatest common divisor of 84 and 162? How could we do it? What do you think? Ponder for just a minute. What do you think you would do if you had to find the greatest common factor of those two numbers? Well, you can probably guess we're going to use the prime factorization. So let's find their prime factorizations. I went ahead and did that already. Here's the prime factorization for 84. You're going to end up with 2 squared times 3 times 7. So that means you need 2 2's, 1 3, and 1 7 to make the number 84. And 162 comes out to 2 times 3 to the fourth. So you need one factor of 2 and 4 factors of 3 if you want to make the number 162. Now, keep in mind what we're looking for. We're looking for the biggest number that divides both of them. So I want to make sure that it divides both of them first and foremost, and I want to make it as big as possible. So let's think about it like this. How did I say it here? Oh yeah, the GCD is the largest factor common to both. The largest power of 2 common to both is 2 to the 1. So here's the idea. This number, they both have factors of 2, but 84 has 2 of them, and 162 only has 1 of them. So if I want a number that divides both of these, I'm going to need 1 2. If I put 2 2's in there, then I'm going to lose this number. I won't be dividing 162 if I put 2 factors of 2 in there, because 162 only has 1 factor of 2. Okay, so we're going to need that. The largest power of 3 common to both of them is 3, right? So this number only has 1 3 in it. This number has 4 3's in it, but if I want to, if I try to include more of these 3's, then I'm going to lose 84. So that's the idea. Okay. 162 doesn't contain any factor of 7, so I can't toss in a factor of 7. If I toss in a factor of 7, then I lose 162. So that means what I need is 1 factor of 2 and 1 factor of 3, and that number will be the greatest common divisor. There you go. So the greatest common divisor of 84 and 162 is 6. That's the largest number that divides both of them. This is a symbol that we'll use. This is sometimes called the greatest common divisor function. You put in 2 numbers and it spits out their GCD. That's why it's in function notation, actually. Okay, so just a little bit word of warning here. Did I type this up? I don't think I did. Oh yeah, 6 is the largest number that divides both. Okay, I'll say the warning right here. So this is a big warning from me to you all, and it's this. You're going to find stuff online that says, oh, if you want to find the GCD, then you pick the highest power of every factor. But then you also have to learn about the least common multiple, and the least common multiple is the smallest number that includes as many factors as you can. So I know that students tend to get locked on the numerals again, and they start looking at these powers here, and they start talking about picking the largest one and picking the smallest one and all this stuff. I caution you from thinking about it in that way. You should make sense of the definition, because the definition is what guides us, right? The greatest common divisor is the biggest number that divides both. That's what you're looking for. You're looking for the biggest number that divides both, and that's it. That's it. And let that guide what you're going to pick from these factorizations. Let that understanding guide you. Don't play around with the numerals, right? Okay. I'll do a couple of these and then I'll leave the rest for you. Actually, yeah. I'll do a couple. So wait, let's do 50 and 350. No, that one's too easy. Didn't we just do 72 and 108? I knew I used those numbers for something back here. Maybe I was just talking about divisibility. Okay, let's do 72 and 108. Why not? So if we want to find the greatest common divisor or the greatest common factor, they're interchangeable, I need to find the prime factorizations first and foremost. So let me do that. I know that 72 is, oh, what was it? 2 cubed times 3 squared? Yeah, that's right. 8 times 9. 8 times 9, that's right. Okay, so this is 72. And what's 108? 108 is divisible by 12. 108 is divisible by 12. It's 9. Okay, let me write this out. 108 is 9 times 12. Actually, the way that I remembered that is because I know 8 times 12 is 96, because 8 feet is 96 inches. That's just from when I used to work in shops and stuff. So 9 times 12 is 108, but this is equal to 3 squared times 3 times 4, which is 3 cubed times 2 squared. Okay. So 108 is equal to 2 squared times 3 cubed. All right. Now I'm trying to find the GCD, so I'm looking for the biggest number that divides both. And what I'm going to do is I'm basically just going to walk through their prime factorizations and try to pick the highest ones that I can. All right, so let's see. What's the biggest power of 2 that these have in common? 2 squared. So my GCD is going to be, I'll say this, GCD of 72 and 108 is going to be 2 squared. First of all, I can't pick 2 cubed because that's too many 2's and I'll lose the number 108. Oops, 2 squared. Then I'm going to go to the next one here. What's the biggest power common to both of those? It's 3 squared. So we're going to add a 3 squared, or I should say multiply by 3 squared in our GCD, and that's it. So what is this number? This is 4 times 9, which is 36. You don't always have to do that, by the way, and I will actually tell you not to. But that's the GCD. So 36 is the biggest number that divides both of those. 36 divides 72. In fact, 36 is or 72 is 2 times 36. And 36 divides 108 also. So that's what we're looking for. And again, what we needed really was this. We needed the prime factorization to make this process easy. All right, and to get the prime factorization, you have to know about divisibility. And to know about divisibility, you have to have all those theorems and tests, and you've got to be comfortable with our numeration system, and everything just builds and builds and builds and builds, right? Okay, I'll leave the last 3 for you to do, so go ahead and take a moment and work on those ones. See, I need my little like working guy. I got to do that before I do the next lecture. How would you do the other 3? Take some time. All right, and now speak out loud about what you computed. How did you compute it? What did it look like? What was difficult? What was easy? What did you notice about number 2? What did you notice about number 3? What did you notice about number 4? All right, now let's move along. Now we're going to talk about common multiples. So we finished talking about these. Now we're going to start talking about those. So the definition is this. A common multiple of 2 or more numbers is a number that is a multiple of each. So we're going to start with this, a common multiple versus the least common multiple. Now, the least common multiple of 2 or more numbers is the smallest number that's a multiple of each. All right, so that's the difference here. A common multiple is a number that's a multiple of both. And the least common multiple is the smallest number that's a multiple of both. And that's what we're going to look for. We need to be able to find those things. And again, prime factorizations can help us immensely. So let's see how this works. What's the least common multiple of 16 and 12? And this is where students usually start to get confused because if you're not comfortable with the difference between a factor and a multiple, finding the greatest common factor and finding the least common multiple is going to be difficult. Remember, multiples of 16 are 16, 32, 48, 72, I think. I think I might be wrong on that one. I'll have to think about it. But 12, multiples of 12 are 24, 36, 48, for example. So the least common multiple, wait, hold on one second. Oh yeah, okay. There we go. So let's do our prime factorization. 16 is 2 times 4, or sorry, 2 to the 4th. And 12 is 2 squared times 3. Now what I'm looking to build is I'm looking to build a number that's a multiple of both. So first and foremost, if I'm going to be a multiple of both, I've got to have the entirety of both numbers in there. So in other words, I can't be a multiple of 16 unless I have at least that many multiples of 2 in there. I'm sorry, that many factors of 2 in there, right? So my LCM of 16 and 12, it's got to include 4 factors of 2. Has to include that. Otherwise, I won't even have the number 16. But here's the cool part. Now that I've already got 4 factors of 2, I've already taken care of the 2 factors of 2 that I need to make 12. But now I've also got to toss in a factor of 3, because if I don't, then I won't have the number 12. So all I'm going to do here is multiply by 3. And that's the least common multiple. That's it. That's the least common multiple of 16 and 12. What is that number? Honestly, I'm not really going to care that much about what that number is, because when these numbers start getting big, it's easier just to leave them in their prime factorization. And also, if you leave them in their prime factorization, it's easier for me to tell that you know what you're doing. So I think, like on the assessment, I say, don't multiply it out because I don't want you to multiply it out. Because if you multiply it out, then I have to refactor it to see if you got the right idea. Um, but this one is small enough, maybe we can do it, right? So let's see, 2 to the fourth is 16 times 3 is 48. There we go. That's the least common multiple of 16 and 12. And again, for this one, it was not too hard to see that it was going to be 48 just when I was counting, right? But imagine these numbers are gigantic. Just imagine they're gigantic, okay? All right, there we go, there we go. All right, so here's a couple examples. How do I finish this here? Oh, yeah, okay, that's right. All right, so I'm going to leave a couple of these for you, but what I'm going to do is I'm going to do number 2. And then these are the other ones that you should do on your own right now or with your group member. But let's see, if I want to find the LCM of m and n there, I need to at least have the number m, so I'm going to need at least this many 5s. Notice this one's only got 1 5, but I need at least 2 if I want to construct the number m in there, or if I want m to be a factor, I should say. So I'm going to need 5 squared, and then I'm going to need all of those 7s, and I'm going to need all of these 13s. There we go. So now you can see that m appears in here, right? M is a factor of this number because m is 5 squared, 7 cubed, and n is in there too. N is in there because you've got 13 squared, and then you've already got a 5 right there for your other n. So both of those numbers are like in there, and by in I mean they're factors. Factors are in, multiples are out, you could say. Okay, so you can try the other ones. In fact, let me put up a thinker here just so that you can think about it, give you a little visual cue. All right, and now that you've worked it out, go ahead and talk out loud about what you did. All right, and then let's move on. So the concepts of a greatest common divisor and a least common multiple can be and are extended tremendously in algebra. So you might actually remember this from algebra class. But we can talk about the GCD and the LCM of products that contain variables. They don't have to be just numbers, right? Because those variables are just placeholders for numbers. That's the idea. So for example, what's the GCF of these two numbers? We're looking for the largest number that divides both. Let's work it out right here. GCF of 3x squared y and 6xy squared. Okay, well, I need the biggest number that'll divide both. So I'm going to go through the numbers and then the variables on their own, right? Okay, so there's a 3 there and there's a 6 there. 3 is all I can take because if I include the 2, that's a factor of 6, I'm not going to be able to divide this number anymore. So it's just going to be 3. Now, let's see, the first number here has 2 factors of x. This one only has 1 factor of x, so I can only include 1. Otherwise, I'll lose this number. That's the whole idea, right? All right, now this number has 1 factor of y, and this one has 2 factors of y, so I can only include 1 of them. Otherwise, I'll lose this number, right? So in this case, that's it. That's our that's our greatest common divisor. This is the biggest number that divides both of these. That's what that is right there. Okay, now let's do the other thing. Let's compare, and let's do the least common multiple. Least common multiple, LCM of 3x squared y and 6xy squared. So I'm going to walk through again, and I need to pick out the biggest multiple. So we'll do the numbers first. I'm going to have to include a 6. I need a 6 in there because if I don't include the 6, then I'm not going to have this number, and it's going to be a problem. All right, now this guy over here has 2 factors of x, and this only has 1. But if I'm going to be a multiple of this number, I'm going to need those 2 factors. So I'm going to go ahead and put those 2 factors in there. And the same reasoning for the y's. If I'm going to be a multiple of this number, I need 2 factors of y to make that work. So, hey, there we go. That's going to be the LCM. So I hope that example kind of clarifies things and explains things a little more there, because that's pretty much what we're looking for. All right. Oh yeah, there you go. Worked it out for you. Okay, so these, I'm going to let you do these, and I think actually some of these are on the activity now that I think about it. Number 4 in particular is a very interesting one. So make sure you understand the difference between factors and multiples when you do number 4, okay? Or sorry, factors and terms. Factors and terms. Make sure you understand that difference before you do that one. All right. Okay, so I think that's it. Yep, let's go to 11C, activity 11C. Let me pull it up here. Okay, so here's activity 11C. It's all about the GCD and the LCM and divisibility. Here, you're just determining if a number is divisible by those using the divisibility tests. Same thing for the second problem. This problem is asking you to make sense of that one theorem about primality where you only have to go up to the square root of the number. So make sure you understand that. And then, yep, there we go. So the last bit is just finding, yeah, is just finding all of those, the GCD and LCM of those numbers. All right, so I'll leave those ones to you. Okay, so I think that's about it. Oop, that's activity B. Yep, that's all it. Okay, so then I'm going to go ahead and say bye again, and I'll see you all at the next lecture, and I'll see you all in the collaboration meetings. Have a good one.